So welcome everybody to the IS High Energy Theory Seminar. So today we are very happy to have Nathan tell us about R-matrices and brane intersections.
Thank you. It's a pleasure to give the seminar. This is based on a project that's coming out in 2 weeks about Mura operators. Let's see. Well, so in one's first course in two-dimensional conformal field theory, one learns that in the holomorphic sector, the generators can be realized in terms of free bosons. Free field formalism, Coulomb gas formalism, Dotsenko-Fatega formalism, goes by many names, and sometimes in certain cases by a product of Mura operators. What do I mean? The most famous example would be this Wn symmetry algebra for SUN Toda CFT. Each factor here is called a Mura operator. It's made up of free bosons, which I called phi1 of z, depending on this holomorphic coordinate z for your Riemann surface. And the two-point function of your free bosons is just very standard. It's just free bosons. This parameter alpha 0, sometimes called background charge, basically gives you the value of the central charge of your algebra. And so the Mura transformation is the statement that if you multiply n of these operators together and expand in terms of differential operators, the coefficient, this generating series, are the generators of the algebra itself. So as an example, for Wn algebra, if I expand this product, well, the first term will be 1. That's trivial. The second term in this case, well, will be the sum of bosons. If I work with an SUN Toda CFT, then this is just 0. It's not too important if it's not 0, just means you have an extra U1 here. The first non-trivial thing is T2. So this thing in terms of free boson, that's called the stress energy tensor. If you just studied Liouville conformal field theory, in the VR-Soro sector, you just have two products, sorry, a product of two factors, and the expansion stops here. For Wn,
so if it's written with only one scalar, you get 0 for T2, because I is less than j.
I is less than j.
So if it's only one value of I, that would be 0.
Yes, right.
And this follows with their two scalars. It's phi1, which is minus phi2. So,
So neutral corresponds to
yes.
that.
Yeah. So since the work of Alde, Gayoto, Tachikawa, it is known that the Wn algebra arises as the algebra of a protected sector of operators on M5 branes in M theory. Various works and constructions, in fact, it's been realized that if I take M5 branes on, well, so here's my background in M theory. For now, C epsilon 1, epsilon 2, epsilon 3 will just be labels. Just think of them as three complex planes. I'll take this C to be a cylinder and C times R. Well, if I put M5 brane in this configuration, so far I just have a 62,0 superconformal field theory living at low energies on the M5 branes. But then if you subject part of your background to what's called a certain twist, the omega background, in effect, if you don't know what the omega background is, think of it just as some process to localize the theory, an alternative to compactification. The theory localizes to a two-dimensional theory on CZ, and this, well, so this epsilon 1 plus epsilon 2 plus epsilon 3 equals 0 constraint. That's a constraint to preserve supersymmetry in this background, so I'll just impose it throughout this talk. But if you put M5 branes in this background, well, you get something that looks like a Carroll algebra living on C. And the work of Aldegato and Tachikawa tell you exactly what this Carroll algebra is. It's a Wn algebra in this case. Yes?
Your omega deformation here is something you can realize geometrically?
Yes, so I mean, it will be in the sense of Costello's work. So it will be this twisted M theory background. So every time you have M theory on a G2 manifold, just some S1 isometry, it will be there will be such a background that you can define. maybe you don't mean this by geometric.
Well, the only geometric construction I've learned now is that when you go around the circle, you rotate other.
Ah, yes, yeah, I see.
You don't,
So what I will describe will turn out to be dual to exactly this configuration. So yes, in the end, here you will not see it in this slide. It is not apparent that this.
so what will we be talking about here?
Oh, here. So here, so this is a construction of Costello called the twisted M theory. It's M theory on a G2 manifold times a three space where you have like certain isometries. Maybe let me go one more slide or two and.
Okay.
Before you go on,
Yeah.
CP and RU, if the epsilon, the omega deformation is localizing us to the origin of
Yes.
three C's,
Yes.
why isn't it localizing to just the rest, the remaining 5 dimensions instead of 2 dimensions?
It is, if you, yes, so it is. So M theory, in fact, in this background, is equivalent. In fact, the definition of twisted M theory, meaning M theory on this background, is a 5-dimensional theory of a certain kind. 5-dimensional, non-commutative. Yeah, so the M theory localizes to 5 dimensions, and then the theory on the M5 branes will localize to some kind of surface defect in this 5-dimensional theory, the 'T type of surface operator. I'll go there very. So a very important work that came out just a few years ago recently conjectured that the Mura operator could be realized by a certain brane intersection. So if I intersect M5 branes with an M2 brane, at each intersection, I think of, well, the algebra of operators that would be protected by this configuration would be encoded in precisely a Mura operator. Then the Mura transformation just corresponds to a brane configuration when you have n M5 branes intersecting a single M2 brane. That's, I'm not claiming that this is I'm not giving a proof, no, nothing, but this is the idea. Now this,
What evidence did they give?
they made various checks at the level of, well, you know, so now you can consider various brane configurations, compute various protected quantities, and so there's a lot of consistency checks of this proposal. But I'll explain in detail exactly how we can get there. My goal today will be to explain that these operators, by the way, the background charge, now I've called it literally a geometric parameter, one of the 3 epsilons. And various generations of this operator are actually universal R-matrices. This is very surprising maybe at first, but these operators are R-matrices of a certain algebra. I'll explain what an R-matrix is. Well, what is the algebra in question? Well, it's the algebra of our M theory background. So what is our M theory background? Well, Costello-Lee defined this twisted supergravity in 11 dimensions, and then Costello defines this twisted gravity in the presence of what he defines as an omega background. As, well, this answers your question. Twisted M theory, you can take this as a definition, is 5D, a certain version that is non-commutative of Chern-Simons theory on the 5 remaining directions with complex gauge group GL1C. Okay. So the M5 branes in this picture, well, they look like 2 surface operators, and the M2 branes, well, they would look like line operators in the 5-dimensional T.
For assuming muscle lines or?
Yes, in this case, yes. So the algebra, that is the symmetry algebra of this twisted M theory, was identified by Costello via a holographic argument. So here is what he calls twisted holography, because, well, what is the gravity theory? In his story, M theory is 5D Chern-Simons, this non-commutative Chern-Simons. So that's the gravity side.
So let me understand something about Costello's twisted M theory. Can I take the standard equations of 11-dimensional supergravity and identify a particular solution and say this is twisted M theory, looking in this background, or is it something else?
Well, you have to impose a certain twist by hand.
Hey, I mean, we can talk about M theory on twisted bundles and things.
Yeah, exactly. That's
So we can, take a four manifold over a circle and take a twisted product.
right.
So then that's a certain kind of geometry. So is that right? So there's a solution of 11-dimensional
Yes.
gravity that
Yeah.
corresponds to twisted M theory?
Yes,
Working
yes.
on that?
I'll say, I believe the solution is just flat space, except that he's got a C star, so it's obviously over 10 times a circle.
Sorry, the solution is?
The solution is just flat space with the topologies indicated. Obviously, all those C stars and R's. But then the crucial thing Costello does is to assume that the superghost, the photonic ghost that you get by quantizing supergravity, has an explanation value at infinity. And what should happen is that you then find that if you study that background by standard methods, you would get his theory, algebra Q exact stuff.
So the bosonic
Ghosts.
But
and the
I don't know this work, but in most of those papers, that's not demonstrated as explicitly as you'd want to as a physicist. There'd be something good that hasn't been done, I don't believe, which would show in a much more direct way.
So look at M theory and the BRST formalism and really show there's a solution of that.
Well, the solution, I've told, the solution is just Minkowski space, except one of the directions was compactified.
And the ghosts have a vector
The
expectation.
ghost has a certain specified expectation value.
These are the ghosts for supersymmetry.
Right.
But then the claim is, if his claim is correct, it should be what a physicist would regard as a much more direct, explicit demonstration than exists in any of these papers that I've seen. But the claim is that if you expand around that background, which is just Minkowski space with the superghost, you'll get this plus two exact stuff.
Thank you.
One thing I want to stress about that is that you're giving an expectation to the superghost at infinity. Just like in Higgsing, we specify the value of the Higgs field at infinity. What happens inside is up to the theory to decide.
So the statement of holography in this context is, well, it has a mathematical formulation, which if you're a little bit familiar with the literature, there's now quite a few papers on it called Kosul duality. And so the statement of holography in this twisted background is a statement mathematically of this thing called Kosul duality, which is some equivalence between certain algebra of operators and certain maps. So I'm not going to go into details because that's going to take us way too far from Mura. But just to motivate what happens, well, the idea here is that, well, what is the holographic argument? Well, I told you that the symmetry algebra on M5 branes in this background is a WN algebra. And the idea is that as you take n to infinity, you should recover the universal algebra of symmetry that, that your operators are supported on. So here, your observables are supported on. So here, the algebra in question would be the affine Yangian of GL1. It's a strange algebra. We'll have a little bit more to say about it. It depends on 3 parameters, but actually just 2, because remember, the sum of the epsilons has to be 0 to preserve supersymmetry. There's another way to get to this algebra, which is via the symmetry algebra on the M2 branes. This is a symmetry algebra known as a degenerate spherical Daha, double affine Hecke algebra of GL-NC. And when you take n to infinity, again, you end up discovering that this algebra is in fact, this limit is stable. It's a valid limit in both cases. And you end up finding the affine Yang-Yan of the parent theory, of the gravity theory. In that sense, this is what is meant by holography.
What's the notation of 2 hats?
2 hats means toroidal. It means a double affinization. It's we'll come back to this. So I would talk about this story just fine, but the problem is that this is the cleanest setup in which I can tell you the story, but unfortunately, the universal R-matrix of this affine Yangian of GL1 is not yet known. So this is a big problem because I promise you to show you that the universal R-matrix of this algebra has something to do with Mura operators. So if I want to match 2 things, I would rather that the thing is well defined on both sides. So I'm going to solve a slightly different problem where both things are defined on both sides, and then we'll take a limit to predict what the R matrix should look like for this algebra. So instead, let's consider a slight modification of the background where the statement can be proved exactly. All I'm going to do is replace this C here by another C star. Seems very innocent. This will simplify our life greatly and result in much more physics. So the symmetry algebra of M theory in this new background now is called a quantum toroidal algebra. Again, it depends on the same three parameters. All I'm going to do is just write them in this multiplicative notation where the epsilons are all here. The product of all q's is 1. That's the same as saying the sum of the epsilons is 0. And this R variable is related to the, sorry, this should be RZ in this notation. I can think of those two cylinders as a torus fibered over Rx times Rp. RZ, sorry, in the notation. And so the radius of these two, the radii of this torus appear in this combination. So that exact radius is the R that appears here. We'll justify it later in the talk, why this exact combination, but for now, take this as a given. This is the background. And that's the background I'll be working with. Now, this is not esoteric science. This is one of the most active fields in mathematical physics, both for math and for physics that has been going on in recent years. One is, what is the quantum toroidal algebra? What are its representations? This is still work in progress. And in physics, what do they mean? So there's a lot of work in progress in this direction. A beautiful review that just came out this December goes into every algebra that I'm mentioning and more, and their relation to each other. I highly recommend it if you want to learn what is the algebras, all their appearance, all their manifestations in the known physics. So in the original setup, as I told you at low energies, well, on M5 brane at low energies, you have a 6D2,0 SUN SCFT, which localizes to a chiral algebra on C star Z. In the new setup, well, I now have a transverse circle, right? So at low energies, I do not have anymore a conformal field theory. There's a scale now. What is the theory? Well, it's known that in M theory with a transverse circle, the theory on my M5 branes with a circle transverse to them is a little string theory, 6D2,0 SUN little string, and it will localize, that's based on a large body of work, not onto a chiral algebra, but to something not conformal called a canonical deformation of the chiral algebra, a QW algebra. So this is just something that you take for granted, but I'm just pointing out that you've lost now conformal symmetry on the theory on the M5 branes. Most importantly for us,
You still have 16 terms.
yes, absolutely. The quantum toroidal algebra has a well-defined universal R matrix. That has been studied very thoroughly by mathematicians. Before I explain what it means and how it relates to the Mura transformation, we need to know a few facts about the representation of the algebra. So what is the algebra? It's an algebra with generators that, if you played around with find the algebras in your life, well, there's a bunch of currents, which I'll write, you can think of these as raising currents, lowering currents, and kind of the Cartan part of the algebra. So the generators are these guys, as well as two central charges and two gradings. So I'm writing the modes of the generators here in terms of the grading. So EK, the modes of this operator, have grading D1 equals 1, D2 equals K, etc. That's just the grading. Now the algebra has relations. This is just to show you how complicated the algebra is. So it's not just nice currents, they're subjected to these awful relations. We will not use them in this talk. So just to give you maybe a picture, if I draw the grading on a Z2 lattice, D1, D2, well, here's all the modes represented here. And in fact, the entire algebra is generated by the modes inside this red cross. Just by using the commutation relations that I get from you, you can actually generate the whole algebra. And why do I draw these arrows? Well, this algebra has a fantastic SL2Z automorphism called Mickey's automorphism, which acts by rotating the picture by 90 degrees. In particular, the grading Z1, the x-axis, is mapped to D2, the y-axis, and so on. So, well, this is a nice algebra, and it should make sense maybe that, oh, okay, well, an algebra that has an SL2Z automorphism, I'm dealing with an M-theory background with a torus, fibered over a plane.
So you demonstrated a Z4, but what about the translations?
I didn't write the translations. They're there too. Yes.
Not obvious from.
Not obvious, no. So the representations that have been studied by mathematicians and physicists, there's some distinguished ones. The so-called vertical representations have central charge C equal 1. So remember, there's two central charges. And so if you fix the first one to be 1, well, there's a bunch of, what it does is actually diagonalizes the Cartan. The Cartan modes now commute, so you can find a basis in which they're simultaneously diagonal. The simplest one to consider is called a vector representation. In this case, both central charges are equal to 1. And a basis, if you want to label the elements of this representation, are famously one-dimensional Young diagrams. Okay, we won't need that, but I'm just telling you if you're curious. Fock representations have a slightly different value of the C transverse, QA, where A can be 1, 2, or 3 to the 1/2. Remember, this is the parameter of this omega background. McMahon representation, you put a random complex number, completely generic, as the second entry. So these are labeled a basis of these representations, these 3D Young diagrams, plane partitions. These are 2D Young diagrams, and these are 1D Young diagrams. Now, if you instead set C transverse to 1, there's only one type of representation really that has been studied thoroughly, called Fock representations in this dual channel, where this time you set QA 1/2 for C. And like the H modes do not commute, but they have the commutation relation of a free boson. So the Fock representation for this horizontal representation is just an algebra which will depend on Q1, Q2, and Q3, but of free bosons. I stress that this relation between Young diagrams, free bosons, in fact, this led to a proof mathematically of the AGT correspondence. So this is a very, very encompassing algebra, and it has many, many dualities, which in fact do lead to the AGT correspondence if you study it carefully. In this talk, I'm only going to deal with two representations, the vector representation and the Fock representation in the horizontal channel.
What's the dimension?
Infinite.
Oh, good.
Yes. Tableaus that can grow as big as you want. So, key point, this has been made by, in a bunch of works, but, and if you're, I don't think I'm going to convince you just yet, but there will be other arguments later. The vector representation, so it's in fact the M2 brane. The representation itself is the brane in this twisted M theory. So when I put an M2 brane in a twisted M theory setup, in fact, I am considering a vector representation of this quantum toroidal algebra. Why? Well, it's going to be very hard to, without doing like some extensive computations, but maybe I can give you some arguments. So I told you that these vector representations, they're labeled by one-dimensional Young tableau. Equivalently, they're also a representation by some difference operators acting on the space of function of Z. So my M2 brane, it's a point on my CZ cross CP. So let's call Z and P the value of the point on that CZ cross CP. This representation, the vector representation, acts, well, by Q3 difference operators. So if I have an operator P that I write as some Q shift, and I choose Q3 here, which will, the choice of the label for the Q will be the choice of where the M2 brane wraps in the 6 complementary directions. Well, I get something where P acting on the function of Z just shifts the function of Z by Q3, okay? So how do the generators of the quantum toroidal algebra act on a function? Well, all these generators, by gamma D1, D2, I mean really like all these guys, right? All of them. Well, how do they act with respect to the grading? Well, Z will be coming out with a power D2 and F will be shifted Q3 to the D1. So what it means is that if I act with gamma 0, 1, I am adding 1 unit of momentum in the M-theory torus along the Z circle. Okay?
But what's the difference between E, F, and K?
What's the difference? They have, yes, so they have
E, S, and K.
yeah, so the grading for E, F, and K was as follows. So the grading for E will produce, if I act with E.
Oh, I see.
On a function of Z, I will produce something that's not the same as if I act with F or act with K.
Well, I'm not understanding the notation. Gamma 1, if I switch the sign of K,
Yes.
and gamma 1 K goes to gamma 1 minus K.
It should be gamma minus 1 minus k, right?
Oh.
Sorry?
The second one should be gamma minus 1 minus k, right?
No, it's 1. It's 1. It's
That's
1.
not what you draw on
Then I don't understand that.
your
How
drawing.
are you getting a difference between E and F in this gamma?
Drawing, you put the F's in a different place than.
Yes.
How do you reduce?
I like Over's suggestion.
Here you draw them at minus 1s.
Yes, so you're right that this is drawn with -1, yes. So, yes, yes,
Okay.
-1. Yes. That's right.
Another question. So this Brane construction is symmetric between Z and P, right? So you
Yes.
equally well think of it as working on functions of P and.
Absolutely, it's a Fourier transform, in fact, that will bring you from, but it will exchange X and P. So the point I just want to make is that, well, the generators are identified with the Z2 lattice of momenta on the M-theory torus. As I told you, you add 1 unit of momentum or 1 unit of Z shift on the torus. So that's either adding 1 unit of momentum along the circle, the Z circle of the torus or the P circle of the torus. Now, something funny that happens in the omega background is that when you add a unit of momentum for P, well, you actually shift Z by Q3. That's an effect of the omega background. This is actually was first studied by Edward and Nikita in a paper where they explain that, like, well, if I think of like the moduli that live on this M2 brane theory in the omega background, well, the action of this generator, what it does is, well, in a dual frame, this will look like a maybe I'll talk about the dual frame at the end. But anyway, so that's the idea. The second type of representation, the Fock horizontal representation, I told you has this central charge, and this, in fact, is identified with an M5 brane in this twisted setup. That is much harder to justify why that has to be. If you can justify it, you have essentially proven the AGT conjecture. It is a lot more work to show that this free boson representation is an M5 brane in twisted M theory. It's a hard problem. But in this representation, the operators, just to give you an idea, look like free bosons. So just vertex operators made out of free bosons. It's A's and A minus that do not commute. They have some Heisenberg algebra that depends on Q1, Q2, Q3. And other than that, it's just literally vertex operators, free boson, the way you know.
What are these little functions on the left?
Yes, they're just functions of Q1, Q2, Q3, rational functions. Rational.
Wait, do they depend on R?
Do they depend on R? Yes. Yeah. So sorry, I should have put Q1 to the R on all of them. Yeah. Absolutely. So now, well, the brane intersection of interest to us is then naturally valued in a tensor product of a Fock representation and a vector representation. Remember that the intuition of Gayotto and Rapchak was to tell us that maybe M2 and M5 brane intersecting in M theory on CP had something to do with Mura operators. And they tried to study the algebra by indirect ways, but well, what does it mean now in this setup? It means that, well, maybe this thing has something to do with Mura operators for the quantum toroidal algebra. But I told you what these branes are from the point of view of the quantum toroidal algebra. They're a Fock representation and a vector representation. So now I need to know how to combine them. I need to know how to take their tensor product. So our quantum toroidal algebra is actually a Hopf algebra. Okay? So as such, it's not only equipped with a product, it's also equipped with an operation called the coproduct. Okay, so the coproduct tells you that you start with an element of the toroidal algebra to a tensor product. I write completed because you deal with so many infinite things. Even though the representations I deal with are perfectly fine, you don't actually need the completed product. Just to be safe, generically, for these algebras, you want to write a completed tensor product because you deal with infinities. And so now with this operation that I have thanks to the Hopf structure, I can define a universal R matrix. Now this is textbook how you define an R matrix for any quantum group. If you've ever dabbled with these ideas, it's literally just an element of this tensor product that in particular has to obey this relation. It's an intertwining relation. For any element of the toroidal algebra, R, coproduct of G, has to look like coproduct in the opposite direction of G, R. So that's true for E, that's true for F, that's true for the Cartan. If you can show that for every generator, and that's true, there's two more relations that didn't write down a little bit. I don't want to overbore you with notations, that's the most important one. You have an R matrix. So what is an R matrix? Well, it's something that provides an isomorphism between two representations of the algebra. You can think of your quantum group, well, as a quasi-triangular Hopf algebra. What is that? Well, we're dealing with something called a braided tensor category, if you want. And one of the axioms of the braided tensor category is that it needs to have some commutativity axiom. Okay? And so what is a commutativity axiom? Well, it's something that tells you something like this. So in a braided tensor category, what gives you the commutativity axiom is an R matrix. Every time you have a quasi-triangular Hopf algebra, you have a braided tensor category, the R matrix provides the commutativity axiom of this category. So our claim, and I'm going to show it explicitly for you, is that the operator living at the brane intersection is the R matrix represented in the tensor product of Fock and vector. So literally, that's the R matrix of this algebra evaluated at those two at this tensor product. Okay, so how would I show this? Well, first, what does the R matrix look like? Well, the R matrix is proportional to this following thing. I wrote ... because you can guess the pattern. It's an infinite sum of raising operators that you multiply. These are the modes of the raising operators, tensored with the lowering operators. It keeps going. There's other factors I didn't write down, which correspond to the Cartan part and the grading of the algebra. They will not matter in this discussion. And now what happens, which is quite beautiful, is that if we evaluate this R matrix on this tensor product of Fock and vector, we find that all terms vanish except the first two. That's quite miraculous, but what happens exactly? Let's do the computation. So every factor here before your tensor product will be evaluated in Fock, and every factor F will be evaluated in vector. Now remember, I told you that the Fock representation is just free boson vertex operators. Okay, I wrote you some generic expression for it, but so you're just a bunch of free boson vertex operator. And on the other side, well, I told you these Fs, well, what do they do? What do they look like in terms of the vector representation? Well, it's remember, the action where I do Q difference operators on functions of Z. And precisely F is this combination. It's this Q shift of this function of Z. Okay? So I can rewrite this. And so then if you actually do the computation, you'll find that all the other terms vanish. Just these two survive. And so if you do the computation carefully and take care of the signs, I can rewrite this thing as 1 minus an operator, which is a free boson operator, where Z here is this Z variable that I put on the other side. I Q3 shifted it, made it part of E. So this expansion becomes literally a current, right? It's the modes times Z to something. And then here you have the Q3 shift operator. Okay. So that's the R matrix in this, it's very simple. So now, what happens if we're trying to go back to the affine Yang-Yan, right? What is this operator constructed? So in the limit to the affine Yang-Yan, the circle S1 decompactifies in the P direction. So I told you that this is, well, if Rp goes to infinity for fixed Rz and fixed M Planck, this R goes to 0, so all of these guys are now going to lose their multiplicative nature and go back to being additive. What does my operator look like in that limit? It looks like R times Z times an operator that you should recognize. It's the Mura operator. So this is the Mura operator of the WN algebra for like one of the bosons. Z here, well, that's just a shift of the zero mode. You can reabsorb it. It's completely inconsequential. That's the lowest order expansion of this operator. Now, if you keep the circle finite, instead of taking decompactifying, the Mura transformation for the quantum toroidal algebra is then a simple product of R matrices. So what we've learned is that in the quantum toroidal algebra, if I have a bunch of M5 branes, put an M2 brane and study the intersection point, I can write each intersection as an R matrix. And so the Mura transformation in this quantum toroidal algebra is just a product of R matrices. If I compute what this thing looks like, if I expand this, you write each R as this operator and you expand, you find this expansion. What is this thing? These are the coefficients of this generating series. They're precisely what mathematicians would define as the generators of a deformed chiral algebra. So it's exactly like in the conformal case.
What was lambda of Z in terms of the free boson?
Oh, it's to write it explicitly, it takes kind of half a page. It's very ugly, but it has a very explicit expression.
Explicit expression.
Very explicit.
Exponential something.
Exponential
Linear
something.
or bilinear?
Linear.
Linear.
Yeah. Well, yes.
It's just a product of vertex operators.
Yes. Yeah, absolutely. So in the remaining time, I'll present a few applications. One, Molik and Okunkov gave a geometric definition of the R matrix for the affine Yang-Yan. There's many definitions, by the way, of the R matrix of the affine Yang-Yan of GL1. One of them, this Molik-Okunkov definition, to this day has not yet been shown to agree with all of the other definitions that exist in the literature. But there is such a definition. And roughly what I'm going to tell you for the purposes of this physics talk is that one realization of this matrix is in terms of free bosons. So when you evaluate this R matrix on a tensor product of two Fock spaces, I and J, again, these are free boson spaces, the matrix should satisfy this kind of nice identity. So this was given as some kind of like consequence of that, a very geometric argument, but it has been used in the mathematical physics literature since then. If you solve this equation for R, you find an expression, an expansion, order by order in the epsilons for what is the R matrix of the affine Yang-Yan of GL1. You can solve this by brute force. And so what I just want to point out is that what is this equation? Well, that's just the Yang-Baxter equation on the space F tensor vector. Now we understand that these operators, you should think of them as R matrices, not in Fock tensor Fock, but in Fock tensor vector. Okay, so M5, M2 intersection. And so if you think of these operators, these Mura operators in the ith space and for the ith boson and jth boson as R matrices, this is just the Yang-Baxter equation. This kind of nicely miraculous way to write down, oh, this is how you find the R matrix on Fock tensor Fock. Well, you're just solving the Yang-Baxter equation on Fock tensor vector.
You have the intersection of 2 and 5.
This is the R matrix of MO at the intersection of 2 and 5. Now, second application, it's nice, we talked about the WN algebra, but we can do much better. It's been, instead of considering these M5 branes and maybe one M2 brane, we can go crazy and consider much more general configurations of M5 and M2s. It's been realized that if you consider LM5, MM5, and NM5 in the specific configuration, you get what's called a vertex operator algebra at a corner. Okay, so this is a construction of new chiral algebras that have really nice properties. You can exchange LMN. There's a lot of triality properties of these algebras. Well, in this toroidal context, you get a Q deformation of all of them. What this construction from M theory really gives you for free, it's telling you that for every chiral algebra that has ever been constructed in this fashion at the corner, there exists a quantum deformation, a canonical deformation in the sense of quantum groups for all of them. Okay? Yes. Not all of these branes can be taken together and preserve supersymmetry. So I can take all of these together, all these M5s and preserve supersymmetry. I might need to be careful not to take all the M2s together. Maybe one set is, so that you have to check that supersymmetry is preserved. Okay, so what does it look like, for instance? This configuration is supersymmetric, it preserves SUSY. If I take LM5, MM5, and NM5 in a very generic assortment, such that I have a vertex operator algebra at the corner on CX, CZ, whatever, and one M2 as before, okay? So I've labeled the M5 branes with colors, and I've written one M2 going through all these M5s. You can again think about the M2, M5 as literally an R matrix in a Fock representation, the Fock representation tensored vector. Remember that for the Fock representation was labeled by QA 1/2, 1, where A was 1, 2, or 3. And so in the talk so far, it shows A equals 3, but I could have chosen A equals 1 or 2. When I choose the other values of A, I get the other Fock representations that for the blue color, the red color, and the one that I talked about before. Sorry, before I talked about the blue, and now I'm adding these like red and green. But again, you can multiply these R matrices together at the intersection point, and you find an expansion. The coefficients of this generating series are the generators of this corner algebra. Now, what's interesting is that when you consider these different assortment of M5 branes, these new ones, the R matrices are no longer just 2 terms. They're an infinite number of terms. Remember, I told you the R matrix looks like an infinite expansion in this E and tensor F. Well, all the terms now contribute. You can sum them up exactly by induction. You can prove that the R matrix on the Fock tensor vector in the first direction actually gives this expression, where the lambdas are the free boson operators, and this Q3 shift are the shift operators of the vector representation. Same thing for the other set of M5. And again, the blue set of M5, that's a really simple one that we started with. That's the one that gives you the usual W algebras.
What broke the symmetry between permuting the 3 colors?
Yes, so by choosing which M2 I'm dealing with. So in this setup, I have one M2 that's preferring the direction 3. So that it's preferring it's totally transverse to the blue M5. Whereas it shares some directions with the red and green, which created a lot of problem in the Gayoto construction, because the Mura operators become pseudo-differential operators with fractional derivatives instead of just
But so how did you find these formulas for the red and green Mura?
Oh, well, so
R matrices.
yeah, so there's two answers. One, there's a Japanese group that took these the conformal form of these pseudo-differential operators and brute force found a Q analog by some. It's actually quite a nice work, but they constructed by brute force a Q analog of what a pseudo-differential operator looks like, and they found a formula that looks like this. But what I'm telling you is you don't need to do that. You just write what the R matrix is in a Fock tensor vector. You'll notice that the second term and the third term has like a factorization property that actually gives you something that you can sum up like this.
So you have the general R matrix and then you evaluate it in this Fock representation?
Yes, so every E is evaluated in Fock, and so you get free bosons on E. And every f is will end up looking like a Q3 derivative.
All the terms contribute, and they sum up to this.
Exactly. So that now you don't think, you just like, what is the R matrix on this? That's a product, and you just go to work and you find this, which agrees with this very, very complicated Q analog construction of Mura operators that that the Japanese group gave in 2021. But you don't need to think. Like, this is literally an R matrix, is the point. So to tell you what they look like in the limit, in the conformal limit, this is what they look like. So now they look like pseudo differential operators. These things are fractional powers, epsilon1, epsilon3 are generic. Only in the blue case do you get something that's really nice and friendly. Here you have to, so you have to, how do you define this thing? Well, you define it through binomial coefficients and the binomial theorem. So you can make sense of this as an infinite series as well. In fact, you will find an infinite series in derivatives if you rewrite this using the binomial theorem. So there is a way to make sense of these operators. That's why you also find an infinite series in this deformed case. This case is much easier though to understand, honestly. It's automatic, it's the R matrix. So what I should say, so there's something important here, right? So there's a conjecture, which to this day has not been resolved, which is in which order should I take my branes? The order matters. If I put R green first and then R blue, I'm going to produce a generating series with generators that look nothing like if I invert the colors and permute the branes. So you have to do a lot of work, and in general, it's not known what to do, to show that all the algebras you generate by permuting all the branes, all the colors, they're actually isomorphic. But the conjecture is that the order of the Mura operators does not matter, that they are isomorphic algebras after you carry out the transformation. But in the Q-deformed picture, this is immediate, because the operators are R matrices. I can permute, I can switch the order at will, and so yes, so I mean, so it has to be true because there are matrices in the quantum Toral algebra. They will be, the order does not matter indeed in the limit. Last application I want to show you is how to rederive all these things, well, just a basic idea, but like how to rederive all these results from a totally different perspective. So I've given you a lot of, we've done some computations, we've seen some evidence, but it turns out you can rederive all these expressions in a completely different way. So M theory on my background, because I have this torus, is the same as type 2B string theory on this background, where the radius R here is precisely the combination I promised to show you at the beginning. That's just basic string duality to M theory. The complex structure of my torus is mapped to the coupling. I have no theta term, no axion in this story. So just a rectangular torus. It's the coupling of type 2B. Okay. So I've mapped this configuration of M5s and M2s for configurations of NS5s and D3s. So now what you can do is, well, from a very different idea, well, every now configuration is a configuration of NS5s. Here I just wrote blue ones, but you can write the green ones and the red ones too, with D3 branes that intersect them. And you can ask to also count BPS operators, but this time there's something nice here. This thing has a description as a quiver gauge theory. Right, so like in type 2B, now I can read literally a gauge theory living on D3 branes. For the picture that I have here, it would be, if I had make a mistake, this gauge theory. And so now you can compute, say, an index counting protected BPS operators. Why? Because on the D3 branes, well, they're supported on C epsilon 3 cross S1. This direction here is topological. In this twisted M theory, nothing depends on it. Okay? And so what is this? Well, if I compute a partition function of D3 brane on this background, I'm computing what's called a holomorphic block, or like a, you know, a half index, or, you know, so it's a partition function counting certain protected BPS operators that live on the D3 brane And in fact, you will capture the operators that live at the intersection with the higher dimensional branes. And so if you do compute partition functions of this theory in this background, you actually rederive these expressions for R matrices. What this tells you is that for all these Hanani-Witten type configurations in string theory, in this background, every intersection is an R matrix. So it's this is true for 3D n equal 4 theories, like here, but it's also true for like 3D n equal 2. If I start adding different type of branes, well, you get different multiplets that you have to compute like the zero modes of strings for these multiplets. But everything will be something that has an interpretation in this quantum toroidal algebra. In particular, every brane intersection should be now interpreted as an R matrix. So, okay, so what do I want to say? So we conjecture that the Mura operator in 2D chiral algebras is an R matrix represented on the tensor product of the Fock and vector representations in an affine Yang-Yan algebra. I haven't told you about the representation theory of the affine Yang-Yan, but it turns out to be exactly the same. It has the same representations, Fock, McMahon, vector. So in fact, it's the natural candidate for exactly what the R matrix on Fock tensor vector should be. It's the Mura operator of the affine Yang-Yan. That's what it should be. So after Q deformation, in the quantum toroidal case, actually we proved this exactly because we have the R matrix. So we computed the R matrix and we showed that it's a Mura operator for that algebra. So everything here, I've worked at the level of the operators, at the level of the intersections, and the algebra of operators at these intersections on the branes. It would also be nice to reproduce these results from the gravity dual side in 5D transaminds. So technically, if you're very good, very strong, and you can do some kind of perturbative computation in 5D transaminds theory with the quantum toroidal algebra or the affine Yang-Yan symmetry. So you're going to compute like certain Feynman diagrams involving bosonic ghosts. You should be able to find the R matrix, the Mura operator realized as an R matrix from the gravity dual side.
There's a candidate for defect configuration.
This has not been a. It's very interesting. Yeah, I mean, I'd love if you have any idea, that would be really. Other supersymmetric brane intersections can be studied. So, for instance, I've told you about M2s and M5s. Well, also M5 and M5s can intersect. That's represented by also an R matrix. It's captured, the algebra of operators at the intersection is captured by an R matrix in a product of Fock tensor Fock. In fact, if you go to the duality to type 2B, every type of intersection here, NS5, D5, so I've only told you about NS5s. To get D5s, well, you know, here I worked in a specific SL2Z frame where all my defects were supported on CZ, but I could have acted with the S duality on the M theory torus and produced M5 branes that equally would live on CP or a combination that are on a curve that is not either just purely CZ or CP, but nonetheless supported on a submanifold of the product of these two. So you can really engineer any type of brane configuration in type 2B. The momenta of the on the M theory torus, they become strings in type 2B. So the generators of the algebra, they're just strings, right? The string, what does it do? Well, it adds 1 unit of momentum in the M theory torus, but in the type 2B picture, it's like adding a fundamental string that or D1 brane, depending on how you reduce and where you consider your momenta to be. And you can also, so the generators of the algebra from this type 2B picture, they're just the D1 or the Mn strings, where Mn is the cycle on the torus that's wrapped. NS5 branes, they're understood here. D5, I told you they're dual to these NS5s. D3s, they're understood, but you can do more. What about the D7 branes? What about 7 branes? They're also Mn 7 branes, where M and N, again, are labels of that distinguish a cycle in the torus. Well, 7 branes, they'll modify the metric somehow. So they're interesting to study. They should be related to McMahon modules, those more general modules I haven't told you about. But certainly there's a very interesting questions here to literally understand all of type 2B string theory intersection interactions in terms of modules of the quantum toroidal algebra. By the way, note that in the original configuration, this duality does not exist. In the affine Yang-Yan, I do not have a torus here. What Gayotto and Rabchak did in their corner configuration, which is a type 2B configuration, they used the torus of phases in the Calabi-Yau manifold. So you have a torus kind of hidden here. And by M-theory type 2B duality, they ended up with these corner configurations where the M5 became D3s. And where the M-theory itself becomes some PQM. But it's very hard to work with this. Once you add this circle, you have a second option to perform the reduction to type 2B. And now we have a description of all intersections as like intersections in weakly coupled gauge theory at low energies. So it's a very nice picture as long as you add this extra circle. Okay. There's still much more to learn. Thank you.
Questions for me?
Yes.
In the Chern-Simons case, I know in 4D Chern-Simons, if you consider the crossing of a Tooft and a Wilson operator, you exactly get some it's called L matrix valued in a Fock. So you get a matrix whose entries are Fock space operators.
Yes.
And that gives rise to the Q operator. And so in this story, you're also saying that you have some Tooft operators in the 5D Chern-Simons and a Wilson line.
Yeah.
Right. So that would be the candidate. Crossing that would be the candidate.
Yes. Yes.
R matrix.
Yes. So you're talking about the one shifted affine Yang-Yan. You're talking about you're not talking about 5D Chern-Simons on R cross C cross C, right? You're talking about 4D holomorphic.
I'm talking about the analog and what's been computed.
Yeah, I see.
4D Chern-Simon, where people know how to get
Yes.
an R matrix valued in Fock tensor standard representation.
Yeah.
From crossing of a Tooft and a Wilson.
Yes. Yeah.
And so you're saying,
Are computations done explicitly?
yeah. So you compute the phase space of a Tooft operator, and then you see. So yeah, it's in this paper of Saebyeok Jeong.
Okay.
So just making sure that in 5D that would also be the.
That's the natural candidate then, yes. Yes.
So about you had these fractional differential operators, the pseudo differential operators. So that, at least for somebody of my generation, that immediately makes me think of KP hierarchies. What do you thought about that?
No, nobody. Yes, it's interesting.
It's epsilon 1 over epsilon 3 would have to be rational. Then if you consider those kinds of pseudo differential operators, then they generate flows, which are known as the KP hierarchy.
Yeah, no, I mean, that's,
I was just wondering.
no, I mean, this is really uncharted territory as far as that, so, but no, that's not, yeah, that sounds, and the rational condition you need it because,
Well,
it seems a little,
usually you want the power of these things to be an ordinary differential operator.
yeah, I see.
Right. At least that's the way it occurred in matrix models. I don't know about,
Yeah, no, here,
I don't know about generic powers.
oh, if we specialize maybe some, yeah, I mean, something nice, man.
All you need is the ratio is rational.
Yeah.
Yes, is it possible to compactify also this extra U direction that you have?
I don't think so. I mean, a priori, like it's well, it's a you can imagine.
Something in infinity there or something.
Yes. It's trying to remember how it works in Costello's construction, but so that's the topological direction. I mean, nothing in the story depends on this coordinate as a manifestation, but what would you do if you compactify it?
Well, then three circles and their shape.
Yeah.
And so on.
Yeah,
You also have a natural 2A description.
sure.
I was wondering about.
Yes. Yes. Well, you have a two-way description in here
The
too.
duality of the 2B.
Yeah, exactly. We're doing 2B on a circle, right? So, where everything wraps
Is
it.
there anything interesting you can do 2A?
Not that I know of. It's not, you don't get new, I mean, it must be something, but, it's not,
Well, if you look at the 2A version of the brain configuration, then you're led to the four-dimensional H theories.
yes. Absolutely.
You're good off getting someone who survives in the four-dimensional.
Yeah, no, okay, so sure, yeah. Yes, so absolutely, yes, you could try to, and again, it's the same algebra. Because you're just using T-duality, so it's not a.
Okay, but I don't remember people talking about these Q, Y, LMN algebras as subalgebras of the operator product algebra, four-dimensional n equals 2 gauge theories.
Right, well, yeah, so right. Well,
You have to take a decoupling limit, don't you?
yes. Right, also, I mean, is it strongly coupled or not? I might need to also test dualizing 2B before I decompactify something, right? Because R infinity will give me a.
I mean, the obvious question is whether it's related to the structures that beam Rastelli at all.
Yeah, so that's an interesting question. I mean, I think, well, the paper that makes sense in this context is their algebra W symmetry in 6 dimensions, where it's very similar in spirit, right, to Yagi or Costello thing. Like you find some BRST kind of operator that you define in some clever way, and then you find some protected subsector operators, which precisely is the brain algebra. That story, yeah, so it's very crucial in that story that you use the conformal symmetry to make the operator. This entire procedure seems completely lost as soon as I introduce this. I break the conformal symmetry, the construction kind of falls apart. I'm not saying you can't find a work, it seems very drastic from the point of view of the Rastelli-Rees construction to try to play these games here, but
surely the connection would be going by taking, again, T-dualizing what you're saying here to 2A.
yeah.
How do you describe branes and human brains?
Very good. I wish I had time to do this, but it's actually there's a more fundamental construction that I have not discussed, which is, well, the quantum Toral algebra is equipped with what's called intertwiners, which literally are maps that go from V1, V2, or like in this case, like say, in the case of say an M2 brane ending on an M5, if they can end on brane. So when they're totally transverse, they don't end. Like they just go past each other. But when they share some directions, they can end on each other. And in fact, they do. And there's some beautiful physics here. So I mean, so you can build networks built out of these intertwiners. So Fock tensor vector to Fock. So if you start with a Fock, and this is your vector, your M2, this is your M5, there's some really nice physics here. So that you can think of this junction as an intertwiner in this algebra, and then there's a dual intertwiner. The dual intertwiner corresponds to, if you want, like putting you don't have to do M2, M5. You can do 5 branes ending on 5 branes, 5 branes ending on 7 branes, anything that's basic. You will rediscover every brane junction that's allowed from, like, you know, your days of like figuring it out, like using hard force, brute force, or so now it's all part, if you want, of this algebra. It's telling you that these intertwiners, they only exist for very certain representations. And the representations for which you can find intertwiners, you have to solve an equation that they satisfy, to intertwine the representations. The solutions precisely describe all the branes that are allowed to end on branes. You cannot have a D1 ending on a D5, so you'll find and you will find nice physics too. I mean, if I think of this as a codimension 2, let's go maybe to the, like some D5 brane, and this is a D3 brane. So some in the 2B picture. Well, the ending of a D3 on a D5 adds like 1 unit of vortex charge. And so the Fock module on the other end will be at a shifted parameter, the spectral parameter. And what does that mean? Well, it means that in the 3D gauge theory, there's a running at one loop of the Trans-Simons level. Like you actually get all these effects from just the intertwining relations of the algebra. So basically, based on junctions, the R-matrix is just a junction phi dual. If I multiply these two things, that's an R-matrix, which is just this intersection. So if you want, like the fundamental thing is really actually just the intertwiner from which you can build R-matrices and everything, if they are allowed to end on branes. The example I described in gory detail was totally transverse branes, so they couldn't break. So that's why I went straight for the R-matrix. But yes, if they're allowed to break, there's a structure called the intertwiner, which captures that. And it captures it exactly for the branes that are allowed by supersymmetry in type 2B or in M theory on this background.
How would you get two ends that meet and then separate?
Two ends that meet?
They come to the intersection point. And then
Yes, yeah, okay. Yeah, I mean, I have to think about, but yeah, so all these processes should be, yeah, okay.
It's like moving from a Higgs bunch to a cool count.
There's some really nice commutative, associative properties to these things too. You can think of a configuration of branes like this, where I have like an M2 and 2 M5s in different ways. You can think of it as gluing an intertwiner to an R matrix. You can also think of it as an intertwiner times a finite distance brane, which is called a screening charge in the algebra. So that's how screening charges appear in this free field realization. They're finite extent D3s or M2s between M5s. And so you can prove this equals this as a statement. And in 3D gauge theory, it looks like computing a partition function in different ways with certain boundary conditions and so on. So there's some supersymmetric physics there, but it's all captured somehow by this miraculous algebra. So it doesn't do everything, but it does a lot.
Any other question? Okay, if not, let's thank you.